All right, welcome back. Pre-calculus, another instructional video. I know you're probably getting tired of hearing my voice by now, but we're almost to the end. There's only really going to be 2 videos this week. We've gotten through everything pretty much I wanted to get through. So we'll do, a couple cute extra things that'll help you out a little bit if you're taking advanced placement calculus next year. Then next week we'll actually do, I'll distribute to you the review sheets for the final exam, even though obviously there's not going to be a final this year. But you want to be prepared, okay? I'm leaving all these videos up over the summer. Don't be the person who doesn't watch the videos and then you come in AP Calculus like, I don't know what's going on. But it's almost silly for me to say that here, because if you're here, you're watching the videos already. So tell your friends, text them, be like, stop being lazy bums and watch Berto's videos, because the views, they're way down, folks. And can I get some likes? I mean, you just watch the video and that's it. You don't even like the video. It's unbelievable. Hey, so let's talk about Riemann Sums, right? And you're like, Riemann Sums, what the heck are these? This is what we're doing today. It should be a not too terrible of a video. The next video, hopefully, should be pretty short as well. This class used to be called Math 11 Honors. Now it's Pre-Calc Honors. Riemann Sums, it's actually named after a famous mathematician, Arthurus Rayman. Really, really intense, fabulous mathematician. And really what it deals with is, how do you get the approximation of an area between a function and the x-axis, okay? You can see in number 1, if you look at your ditto, it wants you to approximate the area between f of x equals x squared and the x-axis from x equals 0 to x equals 2, which is something that you know how to get the exact area of. You know how to get the area between a function and the x-axis. You integrate that function, but then it says using a right Riemann sum approximation with 4 subintervals of equal length. And you might be like, what the heck is going on here? First and foremost, if you want exact area, okay, we know how to do it. If you make like a little sketch of what's going on here, we have y equals x squared, and it's only from x equals 0 to x equals 2. So that would look a little something like that, right? Because this would be y equals x squared. So here, this is x equals 0. We'll say this is up to x equals 2. And we know how to get the exact area, okay? If you want the area, you want to take the integral. In this case, we're going to say from 0 to 2. And look, you could even do your upper minus lower thing. If you want area, it's never bad to be thinking about upper minus lower. Kind of silly here, because you can see the upper function is y equals x squared. But the lower function is just y equals 0, right? So you could say integrate x squared minus 0. That's the upper function minus the lower function, all with respect to x. Be careful with notation. Work is very important. I haven't looked yet at the take-home quest for the definite integral, but at a quick glance, I can see that some people are doing their work. They have the proper notation. Other people slacking off on notation. Don't slack on notation, okay? And obviously, this is the same thing as just integrating x squared with respect to x, which we know is equal to x cubed over 3. And we evaluate that from 0 to 2. Plug in the 2, you get what I did on Thanksgiving, right? 2 cubed is 8, so 8 thirds. Minus 0. We love zeros abound. So we actually get 8 thirds as the exact area there. And if you want that in decimal form, how many times does 3 go into 8? 2 times, okay? So 3 goes into 8 2 times, with what? 2 left over, so 2 out of 3, so 0.6 repeating. All right, so 2.6 repeating. That's your actual exact area over here. But they don't want the exact area, okay? They actually want you to approximate the area between y equals x squared and the x-axis from x equals 0 to x equals 2 using a right Riemann sum approximation with 4 subintervals of equal length. What does that mean? Well, down here, if you get your little sketch going, sketch! All right, we know that here's y equals x squared from 0 to 2. All right, it looks a little something like that. And now we want to approximate the area. And if you remember the first lesson from the definite integral, the reason we draw this rectangle in here is that is what the definite integral does, okay? It actually stuffs an infinite number of rectangles between the function and the x-axis, gets their areas and adds them up. And obviously the number of rectangles can't equal infinity. It has to approach infinity, okay? So this right here is really a limit. And eventually you just get so verschlugen close to what the true answer is that you end up with that exact area. But that's because you're using an infinite number of rectangles, okay? And you might remember the slides that I showed you, in the first lesson. The first one had like 2 rectangles in it, then like 6 rectangles, something like that. Terrible approximations, but it's the way you start, okay? If you're gonna get to like 50 rectangles, first you gotta deal with what you're dealing with like 2 rectangles. So look, if they want you to approximate it 4 subintervals of equal length, that really means 4 rectangles. There are other shapes that are used. Trapezoids are really popular. We won't do the trapezoidal rule this year, but it's certainly something that we'll talk about next year. And if you want to draw 4 rectangles, you always want to draw vertical lines. You always want to draw 1 less vertical line than the amount of rectangles you want. So 4 rectangles, you want 3 vertical lines. And you want to try to make sure the subintervals are of equal length. And I didn't really do the greatest job here, but it's not bad, close enough for government work. This distance right here, this distance here, this distance here, this distance here, they're supposed to be of equal length, okay? And what we really want to do here is we want to get the area of all these rectangles, rectangle 1, rectangle 2, rectangle 3, rectangle 4, and add all those areas up, okay? And that's going to give me an actual approximation. You might look at this and be like, Alberto, these aren't rectangles. Yeah, this is not a rectangle right here, okay? Believe it or not, it's a lot closer to a right trapezoid, but this is curved, so it's not even a trapezoid. You got to square things off. Math world can be very sketchy, a very dangerous place. You got to learn to square off, okay? And what it means is a right Riemann sum approximation is that means you're going to look at each rectangle and you're going to use the rightmost x value to determine the height. See, the base of each of these rectangles, right? We want to get area, so you want to do base times height. This is the base. This distance from here to here, this distance from here to here, this distance from here to here, and this distance from here to here. And all those bases are supposed to be equal, right? Equal length. And really what that is you could even tell me, people think about it, if you have 4 subintervals and you go from 0 to 2, well, each of these distances has to measure what? Very good. A half. Okay, this right here would be 0.5. This would be 1. You add another 0.5, and then you add another 0.5 to that, and you actually get 1.5. Add a 0.5, you get to 2. Easy to do here, not so easy to do in certain other types of problems. This is actually known as delta x. It's just the change in the x values. Had the x values changed from 0 to 0.5, they went up by 0.5. Had the x values changed from 0.5 to 1, they went up by 0.5. There's a formula for delta x, okay? And delta x is always going to be upper bound minus lower bound divided by the number of subintervals. It's going to be b minus a over n. B is the upper bound, which we know is 2 in this case. A is the lower bound, we know is 0 in this case. And n is the number of subintervals, which we know is 4. So we really get 2 over 4, which is equal to 1/2. Same thing as 0.5. That's why you go 0.5 from here to here, here to here, here to here, and here to here. Other problems, you'll have like 6 subintervals, and you go from, 1.6 up to 3, and it'll be a lot more difficult to get what delta x is. Use this formula right here. So look, if you want to get the area of each of these rectangles, you want to take the base, multiply it by the height. Like I said before, these aren't even rectangles. So what's really going to happen is that the base is going to be x values, right? The change in x. The height, that's going to be a y value. And for each rectangle, if you look at the first rectangle, you have a left bound, which is 0, and you have a right bound, which is 5, okay? And since you want to do a right Riemann sum, that means you want to plug in the rightmost x value to determine the height. So this right here, this distance, that's the height of the first rectangle. And if you draw a little vertical line, I'm losing it, horizontal line, you'll get the rectangle right there. It's not so easy to see with the first one because it's kind of smushed in over there. But the second rectangle right here, don't plug in the 0.5 to determine the height. You would do that for a left Riemann sum. Since this is a right Riemann sum, plug in the 1 to determine the height. So this is actually the height right here of that second rectangle. So draw a little horizontal line. You square it off. Okay, and then with rectangle 3, you can see we plug in the 1.5. And then with rectangle 4, you're going to plug in the 2. And now you can actually see that we're going to get an over approximation. When we get the area of all these rectangles and add them up, it's going to be something known as an upper sum, which means you're actually getting an over approximation. It's important to be able to square off appropriately. There are 2 other types of Riemann sums. There's a left Riemann sum. There's a there's a midpoint Riemann sum. We'll do those after this one, and we'll square them off appropriately as well. Sometimes they'll just give you a graph, and they'll want to know, for which of the following functions, they'll give you like a bunch of graphs. For which of the following graphs does a right Riemann sum over approximate the exact area or the integral, this integral right here. And just by squaring off, you could tell whether you get an over approximation or an under approximation. If you want to get the area here, it's going to be really annoying the first time we do it, but we're going to actually come up with an expansion that's going to make the next 2 problems much easier to deal with. So the area is approximately, because it's not going to be exact. We want to get the area of this first rectangle, okay? And remember, the area of the first rectangle is just base times height. The base is delta x, which is 1/2, so I'll put the 1/2 right here. And then the height is always going to be an f of every single time. Since it's a right Riemann sum, you plug in the 0.5 to get the height. If you look at the first rectangle, 0.5 is the rightmost value there, x value. Plug in that rightmost x value, 0.5. This y value right here represents the height, right? This distance here, and that's f of 0.5. A function always represents what kind of values? Y values. If you want a y value that corresponds to an x value, you plug in that x value to the function, f of 0.5. And believe it or not, that's rectangle 1 right there, okay? That's rectangle 1's area, okay? It's just really the 1/2, that's the base, times f of 0.5, which is the height, which is actually a quarter, right? You know, if f of x is x squared, f of 0.5 is going to be 1/2 squared, which is going to be 1/4. Plus, now you might notice the second rectangle, you start the same way to get the area, right? With delta x, the base, which is 1/2, that's the same thing. See, those are the same. That means we're gonna factor that out in the end. But anyway, now to get the height, you want to plug in the rightmost x value because it's a right Riemann sum. You want to do f of 1 for rectangle 2. You know, so that's really rectangle 2's area right there. Rect 2. Okay, and then for the third rectangle, it's like a rest. For the third rectangle, the same base, right? The base is going to be delta x, will be 1/2. They seem to have something in common. Yes, they do. And the height, now it's going to be f of, not f of 1, it's going to be f of 1.5 because it's a right Riemann sum. 'Tis a right Rayman Sum, and that's rectangle 3, rect 3. And now for rectangle 4, I'm going to write it first, rect 4. Woohoo! Rectangle 4, you can see the base, still 1/2, still delta x, it's a 1/2. And the height, now since it's a right Riemann sum, plug in the rightmost x value, the 2, f of 2. You know, sometimes you have to do this. I will do a problem tomorrow where the subintervals actually aren't of equal length. You know, these won't all be 1/2. They'll be different distances. So you're going to have to calculate the area of each rectangle separately. You could do that for every one of these problems right here. But you could really do an expansion. You can see the expansion. All of these have something in common. They all have that 1/2 in common. You could actually factor that 1/2 out. And what does it leave us with? That leaves us with inside here f of 0.5 plus f of 1 plus f of 1.5 plus f of 2. And that right there is really the right Riemann sum expansion. You know, this is an expansion too, but really, you could jump right to this every time. Every time you see a right Riemann sum, or a left Riemann sum, or a midpoint Riemann sum, which is the last one we're going to do today, you could, as long as the subintervals are of equal length, if they're not of equal length, you're going to have to calculate each area separately like we have right here. But if they're in equal length, the delta x is going to be the same for every single one, okay? It's going to have the same base. So you're going to be able to factor out that base. You're going to be able to put the delta x right in front. And then you only need to really worry about the first rectangle. And I know we already have it drawn over there, but I'll kind of draw it over here because you're not going to be able to write these things out every time in graph. It's going to get ridiculous. Sometimes you won't even give the information for that because they won't represent the function algebraically. They'll represent it numerically or tably. That's the most popular way to do these problems. We'll talk about that mañana or a couple days from now. But anyway, if you think about rectangle 1, it's going to start at the lower bound, right? We know it starts at 0. And it ends 1 delta x later, okay? Because that's the actual base right there. And then you think to yourself, okay, it's a right Riemann sum. I always start with delta x. My first f of, just think of the first rectangle. The first rectangle, the rightmost x value is 0.5. So the first f of is f of 0.5. And then you might notice to get from one argument to another, because the number's inside of the argument, right? What do you add each time? 0.5 goes to 1. What'd you add? 1 goes to 1.5. What'd you add? 1.5 goes to 2. What'd you add? You added 0.5 each time. You added delta x each time. So you don't need to actually set up what I set up over here. You can go right to the expansion, and this is what we're interested in. Many times in part 2s, you'll actually leave that information, but you won't here, okay? And in most part 2s, you'll take out the f of part, you'll at least put the values in right there, and we could do that. This is really 1/2 times f of 0.5, okay? That's really just 0.5 squared, 1/2 squared is 1/4, plus f of 1 squared is just going to be 1. Okay, plus f of 1.5, that's f of 3/2. You know, 3/2 squared is going to be 9/4. Okay, and then plus f of 2, which is 2 squared, which is 4. And believe it or not, you could leave it that way on an AP for a free response. A lot of these will be part 1 problems. You actually have to, you know, calculate what the answer is. There were programs for these stuffs. You know, this one right here, you could do by hand. It's kind of annoying, and it's just not what they typically have these days. You'll see the other types of problems you have to do by hand in the next lesson. But you could always do stuff like this. There are cool programs I'll give you next year as well. So you probably won't have to do what I'm about to do right here. But you could just set up this. I mean, you could just set up your expansion, right? The 1/2. Okay, where is it? Can you still see it there? So we got that 1/2, little alpha y equals, fishiquis, 1/2. Yeah, nice job hitting the 2 there, birdo. Okay, and now f of 0.5, well, f is really in y1, right? So you could go over here and be like, alpha 20, y1 of 0.5, plus alpha 20, y1 of 1, plus alpha 20, of, 1.5 plus a little alpha 2 y1 of 2. Make sure you double up those parentheses right there. And we get 3.75 approximately. So this is approximate right here, 3.75. Remember that exact area? Okay, the exact area was 2.6 repeating. And then we said that we would have an over approximation here. It was obvious it was an over approximation by the squaring off that we set up. And you can see this right here is indeed something that we call an upper sum, which they don't really say too much on the AP exam, but you can say that if you want to. It's really, excuse me, but that was disgusting, an over approximation. Great, that's going to go viral. Okay, so an upper sum, something known as an over approximation. And that's it. I know it looks crazy, but you can see when we do the next problem over here, it's a lot easier to do. Same region, okay, but now we're going to use a left Riemann sum expansion. And it's still 4 subintervals of equal length. If they're equal length, you could always set up the expansion. So there's my diagram. Wow, probably the worst I ever drew it in my life, okay, from 0 to 2. And now, you know, with 4 subintervals, so throw 3 vertical lines. Try to make it look like the subintervals are of equal length. It's really up to you. It doesn't make a difference. 0.5 right here, 1 here, 1.5. But now we square off, you know, rectangle 1, rectangle 2, 3, and 4. You could see that with a left Riemann sum, we're using the leftmost x value to determine the height. And that's why I didn't start with the left Riemann sum today. Usually, whenever we do these problems, we always do left first. But look how confusing left is here. The first rectangle isn't even a rectangle because you don't plug in the 0.5 now to determine the height. You plug in the 0 to determine the height. So really, if you draw that horizontal line, you're under approximating there. And from 0.5 to 1, plug in now the 0.5 to determine the height. So here's the height. So now draw the horizontal line, and you'll see the rectangles now ending up below the curve instead of above the curve like they were before. This guy right here, rectangle 3, don't plug in the 1.5, plug in the 1 to determine that height. And then for rectangle 4, plug in the 1.5, this guy right here, to determine the height. And you can see this is going to be a lower sum, an under approximation. You know, every time a function is strictly increasing, a left sum will always be a lower sum, a right sum will always be an upper sum. Things we'll speak about next year. And now when you set up the area, people are like, oh my God, I got to do the area of all those rectangles separately. That was so confusing. It's not confusing at all, okay? Since it's 4 subintervals of equal length, set up the expansion. Start with delta x. Remember, it's the same delta x here. It's b minus a over n. It's 1/2. We did it before. Start with delta x. And then you want your first height, and that's just an f of. Just think of the first rectangle. Rectangle 1 will always start at the lower bound, which is 0 in this case. It'll end 1 delta x later, which is 0.5. Since it's a left Riemann sum, we want to plug in the 0 to determine the height. So the first height is f of 0. Then all you got to worry about is adding delta x to get to the next f of. The next f of is going to be 0 plus delta x. 0 plus 0.5 is 0.5. Plus f of 0.5 plus 0.5 is 1. Plus f of 1 plus 0.5 is 1.5. And I know I'm done there because 4 rectangles means 4 heights, okay? And you'll see a left sum will actually always start with f of the lower bound and always end with f of 1 delta x to the left of the upper bound every single time. A right sum will actually always start with f of, besides the delta x, f of 1 delta x to the right of the lower bound, and it'll always end with f of the upper bound every single time. So this is it. Is that hard to set up? Okay, and it's really just a shifted, right Riemann sum. You can see the right Riemann sum started right here and went up to f of 2. This guy starts right there at f of 0. You know, so if I go to get my answer, which I know, by the way, is going to be an under approximation here, just because of the knowledge that I have of thinking about the squaring off, that's very important. If I get a little second enter going on here, yeah, I don't mean to confuse you too much. You don't really have to worry about this too much. They don't give these types of problems anymore where you got to use the calculator this way. You'll see their programs, and there's other types of problems we'll talk about tomorrow. But this guy right here started with f of 0, but he had the f of 0.5, which is here, had the f of 1, had the f of 1.5, just not the f of 2. We'll make the f of 2 f of 0. I hit enter there, and I get 1.75, which you can see for sure definitely looks like a lower sum. It's not even that it looks like it. We know it. Search your feelings. You know it to be true. We know the exact area is 2.6 repeating. We use the definite integral for that. The fundamental theorem of integral calculus, part 1, version 1. Here, the lower sum really means it's an under approximation. It's an under approximation. Approximate. I get real British when I do these terrible accent. Anyway, under approximation right there. So you can see how much easier it is to do the, expansion right here if the subintervals are of equal length, because the delta x is going to be the same for each of these, rectangles over here. These just represent the heights. When it's subintervals indicated by the data in the table, that's the way they usually say it. We'll do one of those in the next video. That gets a little bit more cheeky. Let's keep the British thing going. It's bloody crazy. But no, it's not nearly as bad as you might think. Let's do one more, the midpoint Riemann sum, which everybody thinks is actually the average between the right Riemann sum and the left Riemann sum. That's not true. The trapezoidal sum, trapezoidal expansion, that's the average of the left sum and the right sum, something we'll talk about next year. Here we're going to use a midpoint Riemann sum. That just means to get the height, you'll plug in the midpoint of each rectangle, which is kind of weird. Okay, so let's draw that diagram again. It's just getting worse and worse each time I draw it. I don't know what's wrong with me. I got to get back in the classroom. Here we'll get those three partitions drawn in right there. We know this guy going to be 0.5, 1, 1.5. It's the same problem. It's the same delta x. Rectangle 1, rectangle 2, 3, and 4. And check this out. Now you're not going to plug in. Let's do rectangle 4 first because it's bigger. It's over here. You're not plugging in the 1.5 or the 2 to determine the height. You're plugging in the number that's directly in between. I'm not going to show this vertical line right here, but that distance is the height. Now you have to actually draw a horizontal line in either direction. And you'll see that a portion of the rectangle is above the the curve, and a portion is below. And that's the way it works right here. If I plug in the midpoint right here, you can see I go a little bit to the left, the horizontal line, a little bit to the right with the horizontal line. With rectangle 2, here's the midpoint if I plug in the x value. Okay, and this guy over here, really hard to see. It's why I didn't start with that. So do the best you can with something like that. And you can see some of it's above and some of it's below. So we won't know just by squaring this off whether it's an upper sum or a lower sum. We'll have to get the answer and then compare it to our exact area. Then we'll actually know. The midpoint Riemann sum freaks everybody out. But look, if it's subintervals of equal length, just start with that delta x like we did before. The only thing you got to worry about is that first f of. And remember, just think about that first rectangle, okay, and that first rectangle starts at the lower bound, ends 1 delta x later, but I'm not plugging in the left x value. I'm not plugging in the right x value. I'm plugging in the x value right in the middle. And some people are like, how am I supposed to know what's in between 0 and 1/2? Well, you know it's 1/4. If you don't, get out of my room. But that could be, wait, not even my room, get out of your room. Get out of the kitchen, wherever you are. Maybe you're in your car or the garage. Who knows? Outside. It's nice outside. Right now, anyway, I'm making this video on Sunday. You're not watching on Sunday. It's not even uploaded to YouTube yet, but it will be. It will be. If you have two nasty numbers, to get the number in between two numbers, just take the average. So just do 0 plus 0.5 over 2. How do you get in between two numbers? You take the average of the two numbers. I'd write this as 0 plus 1/2 over 2. So it's really just 1/2 divided by 2. Only Rourke would divide by 2. The rest of us would multiply by 1/2, and we get a 1/4 that way. Okay, so now I know it's really f of 1/4. Or how about, do I want to put 0.25? Do I want to keep it decimally here? I've been doing it decimally. So we do it that way. It doesn't really matter, but sometimes it gets nasty. If delta x is like 1/3 or something, you don't want to do it decimally, okay? This right here is supposed to be 0.5. You could 0.25, couldn't see any of that. So if delta x is 1/3, you want to keep it as 1/3. So you usually keep fractions, but we'll go, I don't know, decimals one more time. Why not? So f of 0.25, okay, plus, remember, delta x is 1/2, okay, plus add a 0.5 to 0.25, 0.75. Plus f of, add another 0.5, so what is that, 1.25, plus f of, and add another 0.5, I get a 1.75, and I know that's the last one, right, because 4 rectangles means 4 heights, and you'll see that for the midpoint Riemann sum, the left Riemann sum starts at the lower bound, f of the lower bound, ends f of 1 delta x to the left of the upper bound. The right Riemann sum starts 1 delta x to the right of the lower bound and ends at f of the upper bound. The midpoint Riemann sum will actually start 1/2 delta x to the right of the lower bound and end 1/2 delta x to the left of the upper bound. When you write these formulas out in general, that gets really nasty. We'll do it next year. AB calculus, you don't really need to worry about that so much. BC, you need to worry about it a little bit more because it deals with series and sequence and stuff like that. But either way, it's not as bad as you might think. And we'll go for our answer here. Okay, and once again, now we're just going to have to play around in the calculator. It's going to be annoying. I'll just do it all over So a little 1 over 2 is a 1 over 2. A hoo, hoo, hoo. All right, and let's get a little alpha. That was my little freestyle, man. I rhymed. Look, I used to freestyle back in the day. I can't believe I'm saying this on video. It's true. I used to rap with the best of them. Then I head to the stage and I test them in. And when it's all done and said and done, Mr. Berto's going to be the victorious one. Better than a bent, better than a bent. We'll talk about that another time. So what is this? F of 0.25. Doesn't matter. Nobody's watching these videos anyway. All right, Y1 of, we want F of 0.75 plus, alpha Y equals, not alpha Y equals, alpha Tracy over there. So what is the next one? 1.25. Sorry, I'm slowing down here. And then F of 1.75. Okay, and I get 2.625. And you can see, you couldn't tell if that was an over approximation or under approximation by squaring things off. But now you know that the true area, the exact value is 2.6 repeating. So that means that information I had before, and now that I actually know, see, that was the exact area. Now that I actually know what the midpoint Riemann sum expansion is, that means now that I know this is, what, a lower sum? All right, so that's going to be a lower sum, which we already know is an under approximation. Impossible to tell by squaring off. Okay, it's inconclusive. That's Riemann Sums. Very important. It leads into a lot of other things in calculus, and it's a little... like a little bit of grunt work, you know what I mean? Like, it's a little annoying to do this, but the expansions are really not too terrible. So please try the homework tonight. And the homework is really almost like the same problem. It's just with x cubed plus 1. Okay, and you're gonna have 4 subintervals of equal length again, but now it goes from 0 to 1, so you have a little bit different delta x. So download that and check it as well. Rayman Sum expansions. Not something that I even usually put on the final exam. Not that you're taking a final exam this year. Anyway, so do the best you can with that. One more video. It's probably going to be the last one of the year. Like I said, next week we'll be doing final review. Then the week after that, I'm not even supposed to be doing instruction anyway, but I'm going to put out the summer assignment for people who want to take advanced placement calculus. I hope everybody's healthy and safe. If you need to get in touch with me, please do so. Berto, signing off. Adios.